Okay, so good morning, everyone. I'm Daniel, and I'm going to present work on property preserving numerical approximation of a degenerate multiphase fluid flow model with variable densities. This is a talk that is going to be related to the previous two talks. So basically, the idea now is to use the previous idea that Rafa have just presented and apply them to a much more complex model, which is the Cahn-Hilliard-Navier-Stokes model. This is a model of the interaction between two immiscible fluids with different densities. So we have two fluids. The first one that has a density ρ1, second one has a density ρ2 with ρ1 lower than ρ2. And basically, this model combines the Cahn-Hilliard equation and the Navier-Stokes equation for modeling this interaction. This is a model first introduced by Abels, Garke, and Grun in 2012. And in this model, we have mainly four variables. We have the variable u, which is the volume average velocity. We have a pressure that we usually consider to be with mean equal to 0, just to have it uniquely determined. We have the phase field variable, which two different phases. Phase equal to -1 that corresponds with the fluid of density ρ1, and the phase equal to 1 that corresponds with the density with the fluid of density ρ2. And we have the chemical potential. In this model, due to the different densities, we also have a variable density. So we have another variable in this case that satisfies a mass balance equation, but can be explicitly determined as a linear function of the phase field variable using the average and the difference between the densities of the two fluids. And here we have the different terms that appear in this model. We have the strain tensor, the Kimberl-Landau double wall functional, the mobility, in this case, degenerate mobility function. These are well-known terms in the case of the Cahn-Hilliard and the Navier-Stokes equation. And we have some terms that arise when coupling these two models. So we have this term J that is due to the different densities and appear when coupling the model. You consider the densities of the two fluids to be equal, this term vanishes. We have another term related to the capillary forces that appear due to the surface tension. And we have a convection term in the equation, in the Cahn-Hilliard equation, that moves the interface in the direction of the velocity of the mixture. So basically, if we just see the properties of this model, we have that one very important property is that the phase field variable must be bounded in the interval -1, 1, because the variable density is a linear function of this variable, and it has to be bounded between the densities of the two components. It doesn't make any sense from the physical point of view for this density to be either greater or lower than the densities of each of the separate fluids. Also, we have that the mass of the phase field variable is conserved, and as a consequence, the mass of the mixture is conserved. And we have this energy law here with these two positive terms. That means that this energy functional is decreasing. This energy functional basically have these three terms. These two are related to the Cahn-Hilliard equation and makes the phase field variable diffuse all over the domain and aggregate in two different phases. And we have this first term that has to do with the velocity and makes the velocity tend to 0 over time. So the idea is how we approximate this model, preserving all these properties that we have just shown. And the idea is going to be applying the previous results that we have for the Cahn-Hilliard model and the convective linear equation. It's not more than that. Well, it's slightly similar. So here I have proposed this numerical approximation where we use certain discrete spaces for the velocity and the pressure that we're going to define later on. We use P0 for the phase field variable, so piecewise constant functions for the phase field variable, and we use piecewise linear continuous polynomials for the chemical potential. So this is a hybrid method. We're combining continuous finite element, with the discontinuous Galerkin method. If we just focus first on the Cahn-Hilliard equation, we have these two upwind terms that are the ones that Rafa has just introduced. I'm going to recall them in the next slide. And we have here these three terms that are basically some discretization with some stabilization terms that will allow us to preserve the energy stability property. So basically, these two terms in blue are more related to the conservation of the bounds, and these three terms over here are more related to the conservation of the energy property. So Just to define these two discrete spaces, we have a different variety of choices, but we need to satisfy two restrictions. First of all, these spaces must satisfy the in-sub conditions for the approximation to be stable. And second restriction, these discrete spaces have to satisfy this constraint here. So the velocity has to be continuous and zero on the boundary to satisfy the boundary condition. And the pressure space has to contain the piecewise constant function. These two properties are basically to keep the local incompressibility of the variable of the velocity. So we cannot guarantee that the velocity is going to be incompressible, but we just need this local incompressibility to preserve the pointwise bounds. So these are the two upwind formulas that we are going to use. Basically, we're doing upwind. Just in the case of the mobility, as Rafa mentioned, we are just considering the signs of the increasing and decreasing part of the mobility function. And we have a little trick here that's related to the energy. We are doing an approximation of this normal derivative of the chemical potential, taking this normal derivative as the quotient between the projection of this variable in the space of the piecewise constant functions. We take the jump and we divide it by the size of the edge. And we do this in every edge. If we take these structure meshes where the line between the barycenters is orthogonal to the edges, this is basically the slope of the line between the barycenters. So this can be seen as an approximation of the normal derivative. This line is parallel to the uninormal vector. And just to introduce the other terms that appeared in the discretization, we have a center discretization of the term due to the capillary forces. That's basically the one that arises when you integrate by parts, just removing one term on the edges that is a consistent term. This is going to help us for the energy stability. We introduced this first term, the SH1, which is a stabilization term to control the influence of the extra convection term that appears in the model. This is a residual to the mass balance equation. So as long as the density satisfies the mass balance equation, this term will eventually vanish. And we have this other term that is another stabilization term to control the influence of the upwind approximation. So the upwind introduces some regularization, and we need to remove it for the energy stability. As a result, the proposed approximation conserves the mass for both the phase field variable and the density of the mixture. We have the bounds for the phase field variable, and as a consequence, the bounds for the density of the mixture. And due to the stabilization that we have introduced, we have an equivalent energy law to the energy law of the continuous model, but in this case, in the discrete setting. So all these terms here are positive. And as a result, we have unconditional energy stability in our approximation. So now that we have defined a robust approximation that we expect to work in different settings with different initial conditions, different set of parameters, where you're going to see a couple of toy problems, a couple of numerical examples where we have applied this approximation. So we just take square domain, this set of parameters, and this choice for the discrete spaces for the velocity and the pressure that satisfies the constraint that I've mentioned before. We take P2 bubble for the velocity, and we take P1 discontinuous for the pressure. And since the resulting scheme is nonlinear, we need to use some approximation of the solution, and we use the Phoenix X built-in Newton method for that. So first numerical example, we consider two bubbles that are spinning due to a rotating velocity, and we see how these bubbles rotate and aggregate in this region where they are touching each other. If we look at the properties of our approximation, we have that the upper and lower bound are preserved, and the energy is decreasing as predicted by theory. This is a very simple approximation just to make sure that the properties that we predicted in theory are working in practice. And we have another, maybe a little bit more interesting problem where we have a bubble in the middle of the domain, and this bubble is heavier than the medium that surrounds it. So due to the gravitational forces that we have introduced with this term on the right-hand side of the fluid equation, the bubble falls on the bottom of the container, and when it reaches the bottom of the container, it spreads all over the container, and due to the surface tension and the gravitational forces, it keeps coming back and forth, giving this movement. And well, we have, if you see these numbers here, you can check that the bounds are still preserved, so everything's working. And that's basically all I wanted to say. I have the Phoenix X code on GitHub, and I can just send it to you if you're interested. You can reach out to me, and thank you for your attention. If you have any question, I will be happy to answer.